Okay, thank you, Ed, for a very nice introduction. I will try to keep everybody awake for the last talk of the day after all these nice presentations. So, hello, everyone. I'm Alix Volte. I'm a postdoc at the ID9 beamline, and I will present you the project upon which I was hired, which relates to irradiation of electronic devices with short X-ray pulses for aerospace applications. Cosmic rays represent a threat for electronic devices. Actually, the space environment presents an ionizing radiation background constituted of highly energetic particles, protons, electrons, gamma rays, and heavy ions. And moreover, upon entering the Earth's atmosphere, these particles collide with air molecules, giving rise to the so-called cosmic shower, a cascade of X-rays, neutrons, protons, electrons, muons, etc. Radiation effects on electronic devices can be divided into two main categories: cumulative effects and single event effects. Launchers and satellites, which travel through space environments, can be harmed by single energetic particle constituting the ionizing radiation background. In addition, airplanes are typically operated at the altitude where the cosmic shower takes place, and the electronics in their navigation systems is therefore at risk. An ionizing radiation holds enough energy to break atomic bonds and create electron hole pairs in the dielectric material constituting the electronic device. Carriers can remain trapped in the dielectric material and induce an alteration of the device properties, such as reaching of threshold voltage or a short circuit in the oxide layer. Single event effects are macroscopically observable effects induced by a single highly energetic particle depositing energy in a sensitive volume of the device. Charge collection as a result of ionization can cause a change in the circuit operations, such as the bit flip illustrated here on this image after the passage of a particle. An energetic ionizing particle traveling through a semiconductor generates an ionization track by Coulombian interaction in the case of heavy ions and via photoelectric absorption for photons. The energy deposited by a particle in a material is defined as its linear energy transfer, which corresponds to the electron hole density generated along the track. Carriers which do not recombine can travel through the material either by drift as a response to an electrical field or by diffusion induced by a carrier's concentration gradient. These traveling carriers can reach active regions of the device and alter its operations and/or its characteristics. Single event effects can lead to a large variety of radiation damages, which can be either destructive, hard, or non-destructive, soft. For instance, charge collection on a circuit node can lead to, charge collection on a circuit node can lead to a change in threshold voltage and alter its logic state, such as the bit flip illustrated in the previous slide. And this is known as a single event upset, or SEU. On the other hand, high carrier concentration can generate a conduction path, which in the presence of a high electric field can present enough current to create a thermal runaway and induce a permanent short circuit in the oxide layer. This destructive event is known as an SEL, for single event latch-up. Digital devices are most susceptible to single event effects. When it comes to characterization of device sensitivity to single event effects, the challenge is that these are a stochastic mechanism and therefore not easily predictable. Mitigation techniques are usually employed along with preliminary testing of the components. Traditional space equipment was built with explicitly hardened components, which tend to be rather expensive and rare. However, with the recent race for space and the advent of a new space, The trend is to use more and more components off the shelf, or COTS. These components, however less reliable, allow for cost reduction and availability of complex high-performance systems for space projects. With the popularization of such devices, we witnessed a growth in component testing and proving. A common way to characterize device sensitivities to single event effects is to perform irradiation testing with heavy ions. These tests are performed at cyclotron facilities with heavy ion energies around 10 MeV. The drawbacks of this method are that such heavy ions are not able to penetrate through packaging and metallization layers, which implies a specific and demanding sample preparation to be able to reach the active region of the component under test. This becomes more and more limiting for devices involving novel flip chip bonding technologies, or in the case of 3D packaging and stacked dies. The estimation is that in the coming years, the amount of components no longer testable with this technique will increase by around 20% each year. Another disadvantage of this method is the difficulty to obtain beam time at cyclotron facilities, making the testing procedure heavier and longer. To overcome these limitations, recent methodologies have been proposed using photons to generate electron hole pairs in the material and to emulate heavy ions effects. This was first performed using lasers in the visible infrared range and gave satisfying results, although the mechanism of charge creation is different. This method could relieve the difficulty to obtain beam time at cyclotron facilities. However, it does not offer any solution for package penetration, since visible light gets quickly absorbed by the material. An alternative methodology would be to use high-energy synchrotron X-ray pulses. As in the case of laser, irradiation with X-ray beams with highly energetic photons also result in the creation of charges in the device via photoelectric effects. The substantial advantage of X-rays is their ability to penetrate most metallization layers and their large penetration depth in the semiconductor. This would allow to reach embedded components without prior sample preparation, and which would be more representative of space environment conditions. The ID9 beamline is the only beamline at ESRF which provides single X-ray pulses of duration shorter than 100 picoseconds by the use of a fast-rotating triangular chopper synchronized with the RF cavity. This pulse duration is shorter than the commuting time of single event effects, which would allow to emulate the effect of a single particle. Moreover, the beamline has access to ping beam, which with the recent upgrade to the extremely brilliant source allowed achieving photon fluxes of 10 to the 9 photons per pulse. Photons energy from 6 to 24 keV can be reached, which would allow to investigate the effect of photon energy and penetration depth for devices based on different materials. Preliminary studies were performed at ID9 in the frame of an innovation-led long-term proposal. Industrial partners such as STMicroelectronics or CNES or Ariane Group brought their electronic circuits along with test benches to the beamline. And the experiment consisted in screening of electronic devices with X-ray pulses and synchronized detection of single event effects. These studies showed promising results as the X-rays were proved to generate similar single events as heavy ions in the same sensitive areas, and also allowed to build a correlation curve of the effective deposited energy with X-rays and laser. Moreover, packaged and packaged samples with metallization layer could be tested, which confirms the advantage of X-rays in this domain. And eventually, we noticed cumulative dose effects in some cases, which might be an issue for some devices. Looking at the correlation between heavy ions and photons, we can say that both types of particle generate ionization track, leading to unbound electrons in the material, and X-ray beams create similar carriers as heavy ions. GN4 simulations show a different deposition profile between X-rays and heavy ions, the latter being more peaked at a certain depth. Therefore, preliminary studies are necessary to adjust X-ray flux and photon energy to reproduce heavy ion dose deposition. Simulations also show slight differences in ionization, in the shape of the ionization track, which shouldn't be a concern. However, the current beam spot size at ID9 is 25 micron, that we managed to reduce to 5 micron with the use of a pinhole at the cost of a flux reduction. Simulations convince us to strive to reduce the beam spot size to be more representative of a track led by a single particle. And the investigated option would be to use a set of aluminum lenses, which would be designed in collaboration with the optics group at ESRF. As a conclusion, quantification of radiation damage as a routine and reliable characterization of sample represents a huge potential market. Goals for the near future are to define reliable models to predict single event effects induced by X-ray pulses and to correlate to the ones induced by heavy ions. Cumulative dose deposition may have an impact on the circuit response, and it's therefore necessary to investigate further which devices can be tested with X-rays. Finally, one critical step further towards an irradiation facility suited for industrial needs would be to reduce the beam spot size to emulate the effect of a single particle, and this will be the next development on the beamline. I would like to thank my colleagues at ESRF, the industrial partners who performed the experiment and interacted with us to plan the development on the beamline, the IRT NanoElect for the funding, and I thank you for your attention and will be happy to answer your questions.